Namaskar learners. I, Harpreet Kaur, welcome you all on behalf of National Institute of Open Schooling, that is NIOS. As you all know that the motive of NIOS is education for all. That's why we keep on bringing for you our audio and video programs. And today, in this video program, we have brought something very important and interesting under the subject chemistry. We are going to talk about coordination compounds. What are we waiting for now? Let's start learning chemistry. Today we have with us Professor Sulekh Chandra, who is Associate Professor from Zakir Hussain College, Delhi University. Welcome to the studio, sir.
Thank you, madam.
And we also have with us Dr. Rajiv Prasad, Academic Officer Chemistry, NIOS. Welcome you, sir.
Thank you.
And now it's time for us to know about Werner's theory. Why Werner is known as the father of coordinate chemistry and what his theory is all about. So, Professor, please tell us about it.
Yeah. So, I have just told you that Werner was the first chemist who was successfully explained the structure of the complexes and their formula.
Okay.
And that's why he got Nobel Prize in 1913, and that's why he is known as father of coordination chemistry.
Okay.
His observation has been divided into two categories known as postulates and experimental evidences.
Okay.
So, according to Werner, you should be clear that every metal ion has two types of valencies. These are known as primary and secondary valencies.
Okay.
Primary valencies are also known as ionic valency, ionized. They can be easily ionized.
Okay.
And secondary valencies are non-ionizable. Primary valencies are also known as ionic valency, that they are satisfied. Students should understand positively. They are satisfied by the anions only. Cation or neutral molecule cannot be counted for the primary valencies. I'll give you the example. So, they are satisfied by the anions only. And second important is, in modern terminology, primary valencies correspond to the oxidation number of the central metal ion. Okay. Or you can say that if you know the number of primary valencies, you can easily find out the oxidation state of the central metal ion. So, they correspond to the oxidation state of the central metal ion. Since they are not present inside the coordination sphere, so geometry cannot be decided on the basis, or you can say they are non-directional in nature. Now, secondary valencies can be satisfied by the anions or neutral molecules or the cations. In modern terminology, we say secondary valencies correspond to the coordination number of the central metal ion.
Okay.
So, if you know the coordination number, you can easily say the number of secondary valencies. Okay. For example, I have just told you CuNH3 6. It means the secondary valencies are 6. So, this should be clear here. Third postulate has been given. If any anion, I have just told you the primary valencies are satisfied by the anions only. If any anion is present inside the coordination sphere, that will satisfy both primary as well as secondary valencies. But in properties, it resembles only with the secondary valency. So, that is not primary valencies. We generally count them in secondary valencies. These are the three postulates of Werner theory. Now, on the basis of experiment, Werner was able to explain the structure of complexes. As I have just told you, Tazard has synthesized COCl3, 6NH3. He could not explain how many ammonia or how many chloride ions are present inside the coordination sphere. So, first Werner has given precipitation, that is you can say experimental evidences. Precipitation. He has taken the compounds and then add silver nitrate solution.
Okay.
Then he find out how many chloride ions are precipitated out. So, he observed that when we add silver nitrate solution, 3 moles of chloride ions are precipitated out. For example, you can take COCl3, 6NH3 plus silver nitrate. He observed 3 AgCl. This indicates that it means, I have just told you earlier, that any part which is present outside the square bracket will give qualitative test. So, it means all the 3 chloride ions are present outside the square bracket. So, therefore, the formula of the complex should be CONH3 6 within the square bracket and Cl3 outside the square bracket. The second compound is synthesized COCl3 5NH3. Again he added silver nitrate. He found only 2 moles of silver nitrate. It indicates that out of 3, only 2 chloride ions are present outside the square bracket and 1 present inside the square bracket. So here suggests the formula CONH35Cl square bracket closed, then Cl2. Similarly, you can take COCl34NH3 where you can find only 1 AgCl. You will get again CONH34Cl2 and 1 Cl outside the condensate sphere. And COCl3NH3, he founds no precipitate with silver nitrate. It means all the 3 chloride ions are present inside the condensate sphere. Okay. So you can easily say that CONH33Cl3. So by using this experiment, you can easily find out the formula of the complex. You can take any complex. By using this experimental evidences, you can easily write down the formula of the complex. Second evidence is he has taken molar conductance. And molar conductance are the fixed values that depends number of the ions present in the solution. Okay. For example, complex will be always single ion. Suppose you take CONH36 Cl3, it is going to ionize like this: CONH36 3 plus, that is the 1 ion, plus Cl3Cl minus 3 ion. The total number of ions will be 1 plus 3, 4 ion. Okay. If number of ions are 4, then conductance will be around 400. Similarly, if the number of ions are 5, it will be 500. Number of ions are 3, then conductance will be around 250. Similarly, if 1 to 2 number of ions are there, then conductance will be 100. So by calculating or by finding the conductance, again you can easily find out how many ions are present outside the condensate sphere. Okay. So he has taken 2 evidences mainly.
I'm sure learners have understood the Werner's theory, and you are also jotting down the important points, because let me give you a hint. This theory is extremely important from your examination point of view. And now something very important and very interesting for all of us to know. Dr. Rajiv, let me ask you a question. There is an agency with the name IUPAC. What does it stand for and what it does?
It stands for International Union of Pure and Applied Chemistry. That is the union which decides how to give the IUPAC name of the complexes or organic compounds also. And these rules are followed all over the world, you can say. So these are the authority to decide the IUPAC naming of different complexes and organic compounds. Okay. So to understand how to start IUPAC naming of these complexes, there are certain rules we have formulated. These rules says that when we have to give IUPAC name of a complex, the first step we have to start to give to find out the oxidation number of central metal ion. That is the first step. Okay. Suppose the example CONH33Cl3. So in this complex, our first motto is to find out the oxidation number of central metal ion, that is the cobalt. When we calculate the central metal ion, its oxidation number, then comes to the naming of ligands. What are the name of ligands? What are their number? Their rules are in this way. In this process, first we have decided the oxidation number. What is the oxidation number of central metal ion? Now, when we start naming of the ligands, we have to use alphabetical order. Suppose there is chloride ion and there is ammonia, also both are ligands. So we have to give the name first ammonia and then chloride. To naming these ligands, there are certain rules. I am telling you that first step, the naming of central metal, their oxidation number determination, then the naming of ligands, naming of their number, as a mono, tri, tetra, penta, hexa. But in case of halogens, suppose it is chloride, bromide, we have to use chlorido, bromido, iodo. And in case of bidentate ligand, we have used the number. Suppose there is 2 bidentate ligand, 1 base, tris word. These are the common terms which we have to use to give the IUPAC naming. Third portion is that when we give the IUPAC name, first we have to write name of ligand, then come to the name of central metal ion, then comes to its oxidation state. And last we have to use another rule, that name of central metal ion, that iron, cobalt, nickel, what will the central metal ion? How we have to write? If the complex is an anionic complex, suppose the charge comes to the negative, after the ionization when you split the complex. In case of anionic complexes, the name of central metal ion ends with ATE. That if it is iron, we have to use ferrate. If it is cobalt, cobaltate. If it is nickel, nickelate. In this way, in case of only anionic complexes, this is the rule. We generally we cannot write iron. In case of neutral complexes where there is no overall charges on the coordination sphere, we have to name the central metal as it is. If it is iron, it is copper, it is cobalt as such. In case of neutral cationic ligands, we have also used the same process. Iron is iron, copper is copper, silver is silver. Because basically you have to take care that in case of anionic, the name of central metal atom will ends with ATE. That is the most important thing. And the general trend naming the epic rule, first I have explained you that the oxidation number, finding of oxidation number of central metal, then naming of ligands, their numbers, and then central metal, name of central metal, their oxidation state in Roman words in bracket, and then if there is any anion or cation present before or last of the coordination complexes. Suppose one example I am giving you, that in case of complex chromium En whole 3 and coordination sphere, and then Cl3 is given. So we have to name in this complex in this way. First we have find out the oxidation number of chromium in this complex. So oxidation number will come to 3, and the ligand is ethylene diamine, that is the neutral ligand. So as the number is given 3, so we have to say tris. Then we in the bracket we have to write tris, and the bracket will start with the ethylene diamine. This indicates the 3, En whole 3 is written, that 3 we have to not write here tri, we have to use tris, tris. Then the name of central metal, that is chromium. As the complex indicates, Cl3 is outside the coordination sphere. It will ionize as Cl3 minus. So overall the charge on the complex will come 3 plus. That means it is a cationic complex. So we have to write the chromium. And after that its oxidation number in the bracket Roman word we have to write 3. So overall we have completed tris, ethylene diamine, chromium, 3, and then Cl3 is present outside the coordination sphere. So we have to write chloride, not its number, only chloride. So this is the sequence we have to follow to give the epic name of the complexes. One important question I just also want to explain something, sir. Suppose our complex is chromium hexaamine and overall 3 charges given. So what should the naming of this epic name of this complex?
Now students or learners should be able to understand clearly about this naming. As Dr. Rajiv told you, there are certain rules, but something you should also know. Now first of all, as Dr. Rajiv told you, that we should be able to find out the nature of the complex. The nature of complex is, complex may be positively charged, may be negatively charged, or may be neutral. The 3 types of complexes are there. Neutral means, because generally students confused here, if suppose we take K4FeCN6, it is not a neutral complex. Students should be clear, because this has no charge. But since potassium is present outside the coordination sphere, so overall complex will have 4 negative charge. So this is anionic complex. Similarly, we take CONH3,6Cl3. Again, it is neutral, having no charge. But if you see the complex, complex will always cationic. It will have 3 positive charge. Because generally student confused, because sir, ये तो neutral complex है, not a neutral.
There is no charge.
No charge. Now neutral means that suppose you take NiCO4, it has no charge. Neither nickel is 0, carbon monoxide is also 0, so they are having no charge. That's are known as neutral complexes. One more important point is the complex names should be written always in single word. CONH3,6, 3 plus. So this is, you should be write down hexaamine, chromium 3. You should be, ये नहीं रखना चाहिए. This is first you take hexa, then space.
It should be
then,
continuous.
Then it should be a single line, complex name. So complex name should be a single word. This is the most important. Secondly, Rajiv already told you that use alphabetical order. Here again is sometimes the student confused. Suppose if 4 ammonia is there, then you shouldn't say we should see in T. No, because we have to see the ligands. Ligand is amine A. So you have to see the what type of ligand H. Ligand you have to see the name of ligands, not the number of ligands. This is the most important. Generally, in case of anionic ligands, we replaced E by O.
Okay.
Sulfate, sulfato, sulfide, sulfito,
Okay.
or acetate, acetato. So you can put generally, but there are few examples where you can pay to both the ways. Generally use IDE, chloride.
Okay.
Chloride can be written as chloro as well as chlorido. Similarly, bromide can be written as bromo as well as bromido. This one should be clear. Fluoride, fluoro or fluorido.
Okay.
Or iodide, iodo or iodido. This one can easily write down the name. Now for neutral ligands, except 3. I am repeating again, except 3. If ammonia is there, write down AMMINE. For water, aqua. AQUA.
Okay.
For carbon monoxide, carbonyl. And another is NO, nitrosyl.
Okay.
After these 4, all the naming of neutral ligand will be given as such.
Okay.
Suppose ethylene diamine will be called as ethylene diamine. Or you can take triethylene diamine will be called as triethylene diamine.
Okay.
Arsine will be called as arsine. Naming remains same except these 4. One more category is there, although I don't think so in the syllabus or not. Cationic ligands are also there. So for example, NO plus, because NO plus creates some problems here. So if you write down NO, you consider NO is a cationic ligand, then you put nitrosylium, NITROSYL, put IUM. Then you take this is, then for example, I am repeating again here. In such cases, if you consider positive ligand, the oxidation instead of central metal ion will change.
Okay.
For example, you take NaCN5NO. If you take neutral ligand, then the oxidation number of iron will be here. Again, I am repeating. If you take NO is a neutral ligand, then you put here CN5, iron 3, that is 2 minus sign, iron 2 if you take, then 3 minus sign. If you take one positive charge, NO plus, then one positive charge is there, then only 4 cyanide will remain. So if you take iron 2, so then become 2 plus.
Okay.
So similarly, iron 3, you take 1 minus charge.
Okay.
Now, the one more category is there. I'm again addition, that numbering of ligands.
Okay.
There are 2 different ways. One way is ligand do not have di, tri, tetra in their name.
Okay.
Then you take one ligand mono. If there are 2 ligands, bi or di, 3 ligand tri. If the ligand themselves have di, tri in their names, then you can now use di or tri so on. Just for example, Dr. Rajiv told you ethylene diamine. Di is already present in ethylene.
Right.
So you put tris, the COEN3 tris, ethylene diamine. One more category there, sometimes it is confused here. I have just given the example just now where only either cation is complex or anion is complex.
Okay.
There are certain compounds where both anion or cation are complexes. For example, you take CuNH3,4, CuCl4. Both are cationic complex, anion is also complex. There is no change in the naming. First species will always have positive charge. Second species will always have negative charge.
Okay.
So first, as I have just told you, CuNH3,4, 2 plus. That is tetraamine copper 2.
Okay.
Then CuCl4, it receives 2 negative charge.
Okay.
So tetrachlorocuprate 2. Cationic complexes are there, cationic neutral. There is no change in the name of the central metal ion. Cobalt remain cobalt, nickel remain nickel. But if complex has negative charge, then you should add ATE, cobaltate, nickelate, zincate, or vanadate, ferrate, so on.
I hope our learners have understood about the IUPAC naming, and it's very important to follow the rules if you want to give your compounds a correct name. And now something important. Yes, there are so many important things in this chapter. Professor, please tell us about the valence bond theory.
This is also comes under the category of bonding in complexes.
Okay.
Different types of methods are there, but we have to concentrate first only valence bond theory. I think I have already studied valence bond theory in chemical bonding. Similarly, valence bond theory was given by, this is Hunds and Mulliken.
Okay.
Now, this theory is based, actually from where this theory is originated.
Okay.
Actually, when complex was synthesized, there are two complexes having same metal ion in same oxidation state, only ligands were different. For example, CONH3 3+ and COF6 3-. When the magnetic moment of these compounds were found, it has been found that one is diametric, other is paramagnetic in nature. It was the scientists were very surprised why it is so.
Okay.
Because Pauling was the chemist who has given the idea of chemical bonding. Now, Pauling was aware only that on the basis of chemical bonding, he has tried to explain the nature of difference in the bonding. According to Pauling, he has tried to explain since fluoride is the more electronegative nature as compared to ammonia. So, cobalt fluorine bond should be ionic and cobalt nitrogen bond should be covalent in nature. So, covalent means sharing of electrons becomes diamagnetic and ionic means transfer of electrons becomes paramagnetic in nature.
Okay.
Now, in science, without experiment, nothing is true.
Yes.
So, same Pauling has tried to explain, he has synthesized the compounds by taking the another metal ion, but he is surprised to see that they have same magnetic moment. For example, NiNH3 6 2+ and NiF6 4-. And he found that both the compounds having same value of magnetic moment. So, his idea has been rejected.
Okay.
He himself rejected his idea.
Okay.
Now, Huggins was another chemist who has explained given the idea of inner and outer orbital complexes.
Okay.
Inner and outer means, because I will give you the brief this introduction about the inner complexes. Students should be clear, N-1D2 NSNP3. It means 3D. If 3D orbital is used for hybridization along with 4s and 4p, you can say D2sp3.
Okay.
That is called inner orbital complexes.
Okay.
So, we take 5d orbitals, 3d orbitals, then 1 s orbital and 3 p orbital. Suppose you take cobalt. Now, in case of cobalt CONH3 6 3+, the oxidation state of cobalt is +3.
Okay.
Therefore, the electronic configuration of cobalt 3+ should be 3d6. So, there are 5 electrons, sorry, 5 d orbitals are present here. Now, since two d orbitals are utilized for hybridizations, so we have only 3 orbitals are available, and there are 6 electrons. So, all these 6 electrons are get paired in 3 orbitals, and so you will find there is no unpaired electrons. Therefore, cobalt, that is, you can say hexamin cobalt 3 is diamagnetic.
Okay.
And COF6 3- NP3 ND2 means if 4s, 4p and 4d orbitals are used for hybridization, then you can say sp3d2.
Okay.
If this is the case, these are called outer orbitals.
All right.
So, in case of fluoride, he has suggested the complex will be outer orbital. 3d orbitals, 5 electrons will be intact as such.
Okay.
5 orbitals available, they are distributed 1, 2, 3, 4, 5. All the 5 are found to be unpaired, and 6, one more is paired, so 4 unpaired electrons. So, COF6 3- having 4 unpaired electrons and CONH3 having no unpaired electrons. Therefore, you can say we can clearly explain on the basis of inner and outer orbital complexes. For learners, I will give you the idea here because most of the students confused. Which will be inner orbital complex, which will be outer orbital complex. This statement I am giving only for 3D block elements. For 3D block elements, and they metal ions should present in same oxidation state. Same metal ions should be same and present the same oxidation state. Then D1, D2, D3.
Okay.
Whatsoever the ligands, complex will be always inner orbital. The students should be clear here.
I want to ask you, sir, that what are the applications of coordination compounds in our everyday life? We are using different
As I
complexes.
have told in the beginning, that complex plays a vital role in your life. I'll give a few more examples here. This is the most important part, is that if you are perform qualitative analysis. In qualitative analysis, you cannot perform without complex formation. You want to test for the copper. You have to prepare, this is copper, hexacyanoferrite.
Right.
If you say second B group, we have to add yellow ammonium sulfide to separate them, because second B group radicals generally form complexes. So, they are soluble, and second A group radicals do not form complex, they are insoluble.
Okay.
So, we can separate them easily. Third represents iron. I think you are well aware that when you got at potassium ferrocyanide, you get partial blue color. that is ferroferisanide. Similarly, you can also explain aluminum. Aluminum also form complex with aluminum reagent.
Okay.
So complex play an important role, first in qualitative analysis, second in medicine.
Okay.
In medicine, I have just told you the EDTA is used as an antidote for poisoning of mercury as well as lead. Now here, generally question is asked, can we use EDTA? No, because EDTA is not soluble. So we have to use either sodium salt or calcium salt of EDTA, which is soluble. So if anybody inhale mercury, you ask him to drink this EDTA solution, and after some time he will be okay.
Okay.
Similarly, sodium nitroprusside is used to lower down the blood pressure during surgery. So there are a lot of organic coating compounds used in medicines. Again, extraction. We want to extract gold or silver. We have to use complexes because you will prepare AgCN to Na, AgCN whole twice complex, or AuCN whole twice, that is complex. Because they are soluble, so they are separated from the rest of the impurities, and you can easily separate them. So there are a lot of applications with complexes in every field of the life. I already told you, chlorophyll, hemoglobin, without them, you cannot survive.
And now, Dr. Rajiv, would you like to conclude it?
Yeah. To our listeners, I want to say that this coordination compound chapter is very interesting. If you go through getting the basic concepts we have mentioned here, and the IPEC naming, the valence bond theory, and the Werner theory, these are the most important part from which the most of the questions are asked in the examination. So if you have any queries related to this, you can send us email, and we can help you in a big way. And the valence bond theory and its applications, they are also important topics. So these are the important concepts we have provided you.
Learners, I hope you have understood this chapter of coordination compounds. It is very interesting and very important from your examination point of view. Are you jotting down the important points? I'm sure you are. If you have any queries, you can always email us. With our best wishes, and be a successful self-learner. Apart from these video programs, you can also listen to our audio programs, which we call live and interactive personal contact programs. Yes, they are live. You can listen to them through our web radio known as Mukt Vidyavani, and they are very much interactive because we want your participation in those programs. You can always call us in the middle of our audio programs. You can speak to our experts, you can raise your questions, and then of course you will get your answers. So we wish you all the luck once again, and with this, it's a wrap. I, Harpreet Kaur, take leave of you from the studio of NIOS, and I thank both my experts, Professor Sulekh Chandra and Dr. Rajiv Prasad, for their valuable contribution and time. Good luck, goodbye.